Okay, here we are, chapter 4, the introduction to motion. Now we get to the real physics. Now we get to the good stuff as we get to learn about motion. The first several chapters have been about the skills we will need in order to learn physics effectively. Now we get to the real physics. So this is chapter 4. It's actually the last chapter in the first unit. So we'll have an exam over chapters 1 through 4. Um, um, Upcoming here shortly. You can look at your schedule for the date for that exam. So we're going to be looking here about motion, and we're not going to talk as much in this chapter about the causes of motion. That's going to be more subsequent chapters, but more of a description of motion and our ability to predict where something will be based on the motion that it currently has. So the first thing we have to do is define what is motion. So are you moving right now? Are you moving or are you not? And as you think about this question, there are several approaches one can take, right? You can say, well, I'm sitting in a chair looking at a computer screen, so I'm not moving right now, I'm sitting still. Or you can take the approach and say, well, my heart is beating, so the blood is flowing through my veins, so in that sense, I'm moving. Or you can sit there and comment on the fact that the earth goes around the sun, or the earth goes around on its axis, and therefore you are moving. But my challenge, my question to you is, what evidence do you have that you are moving or that you are not moving? What is motion at its core? And if you were in class with me, we'd have this big discussion about how do you know that the earth revolves, and we would talk about the sun and the sun rising in the east and setting in the west. But then we would ask, well, doesn't it look like the sun is the thing moving? I mean, that's what humans thought for many years, was that the sun moved, and the sun moved across the sky. So what makes us think today that it's actually us moving and the sun sitting still? How do you interpret the information that we get from nature? How do we interpret the data, and why is one interpretation better than another? If you go on vacation this summer, say you're driving, say I'm driving on vacation this summer with my wife and my family, and we're driving down the road. Are we moving or are we not? And you would say, well, of course you're moving. You're driving down the road. And it's true. We would look out the window. We would see trees flying past. We'd see fences moving past. We'd see bridges and things moving. And therefore we would assume, because we think of those things as stationary, that they're sitting still and we're actually moving. So some of that comes to common sense, right? Trees themselves don't move along the highway at 65 miles an hour. So if it looks to me like a tree is moving, it must mean, in fact, that I'm moving instead. But I go on this trip and we're driving around, and my wife is still sitting right next to me in the passenger seat. Her distance from me is not changing. So relative to her, I'm not moving, but relative to the road that I am. So we come up with this understanding that in order to define movement, we have to have a reference frame. We have to compare it to something, right? So if I ask you this question on an exam, are you moving? And you say yes, you're going to be wrong. And if you say no, you're going to be wrong. What you're going to need to tell me is that it depends. It depends on what you're being compared to. Again, this example of me driving down the road in my car, relative to the road, compared to the road, I am moving. Compared to my wife or the child sitting 2 feet behind me, I'm not moving, because my distance to them is not changing. And that's really what movement is. The distance or the displacement we are from some reference point is changing, right? As we sit, as you sit in the classroom and I walk around from the teacher desk and start coming towards your desks, the distance between me and you is getting shorter and shorter, and we interpret that, we define that as movement. So we have to define our frame of reference, right? What are we referring to? What is our movement going to be referenced? So relative to the surface of the earth. So if I'm sitting on my chair in front of my computer right now, giving this lecture, relative to the surface of the earth, I am not moving, right? The surface is staying the same distance from me. I'm staying above the same point on the surface of the earth. I am not moving relative to the surface of the earth. Now, relative to the axis of the earth, I am, right? The earth spins around on its axis once a day. At this latitude, we have the earth has a radius of several thousand kilometers, and so we are actually traveling quite quickly at this point, not quite 1,000 miles an hour, but more like 700 or 800 miles an hour as we go around that circle in just 24 hours. So I am moving relative to the axis of the Earth. I'm moving relative to the sun. I'm moving relative to the sun, and the whole solar system is moving relative to the center of our galaxy, the Milky Way. So it is very important that we have a frame of reference to consider. Now, all that wonderful discussion about what is movement and what isn't movement, and we're going to simplify things in this class, and we're going to define our frame of reference for the most part to be the surface of the Earth. So when we're talking about tennis balls or throwing things through the air, we're usually going to be talking about the surface of the Earth being our frame of reference. We will get into a couple of chapters, chapter 9 in particular, when we'll talk about circular motion, and chapter 11 when we'll talk about satellites orbiting the Earth, and then we'll treat the center of the Earth as our frame of reference. But for the majority of this course, we're going to be treating the surface of the Earth as our frame of reference, which again is the frame of reference that you and I live in and think about most of the time. So this way our common sense as to is there motion or not will be valid most of the time, right? If I'm sitting still in a chair, then I'm probably not moving. Now, if my chair has wheels and somebody's just giving me a push from behind, then even though I'm sitting in a chair, I will be moving relative to the surface of the Earth. Again, it's all about that frame of reference. So how do we measure? Now that we've defined movement, how, not all movement is the same. So how much movement is there? And the thing we use to measure this is velocity. Now, we've already talked a little bit about this relationship between speed and velocity. So speed is the more basic thing, but it's a scalar, and we want to talk about velocity, which is a vector. So a speed is simply a rate, and we're going to talk quite a bit about rates in this chapter. So we need to take a moment and think about what a rate is. The rate at which something occurs is simply how much of something happens in a certain amount of time. Rates are always something divided by time. That might be dollars per hour, right? What is my pay rate? Do I get paid $11 an hour? That's the rate at which I get paid. So my total paycheck depends not only on my rate, but also on the total number of hours I work. In a similar way, speed is how much distance or displacement is occurring in a particular amount of time. So when we say 55 miles per hour means if we continued at this rate for an entire hour, we would go 55 miles. We don't have to stay at this rate for the entire hour, but that is the rate at which we're covering stuff, right? I mean, if you go to your job and only work a half an hour, they don't pay you $11, they pay you $5.50 because you only worked for half of an hour. But it is the $11 an hour that's a rate, and it's 55 miles per hour that is the speed or the rate at which we cover distance. But again, that's not good enough for us. We want to have that rate, and we also want to know the direction, right? So sometimes I ask my students, Kansas City is 300 miles away, and if we drove toward Kansas City at a speed, an average speed of, I screwed it up. Oh well, if we drive toward Kansas City at an average speed of 60 miles an hour, it would take us 5 hours to get there, right? 300 divided by 60 is 5. But I usually ask the question more vaguely. I say, Kansas City's 300 miles away. If you average 60 miles an hour, how long will it take you to get there? And everybody says 5, and I say, no, you're all wrong because you're driving east. And they all look at me cross-eyed and say, what do you mean we're driving east? And I said, well, I didn't tell you what direction you were going, and that's why speed's less useful and velocity is more useful, because the direction we are going matters. But I screwed it up the first time I started saying it here, and I said towards Kansas City. Well, towards Kansas City is a direction, so then you could be comfortable in saying that the answer was 5 hours. But 35 miles an hour south, 55 miles an hour east, 55 miles an hour towards St. Louis. All of those would be vectors because there's direction included. It's not just a rate at which we cover distance, but it also includes direction. And again, velocity is a vector, and we represent vectors with arrows because the arrow shows direction, and vectors have to show direction. So I have just a couple of them around here. This one up here in the upper left is a velocity, 5.4 meters per second. Distance over time, right? So meters per second is what we're going to use a lot in this class. Meter is a much shorter unit of distance, time's a much shorter unit of time, or seconds a much shorter unit of time. We'll use miles per hour some, but meters per second more often. This one is an acceleration. We'll talk more about that later this lecture. This one's momentum, which we'll get to in chapter 6, what momentum is and how that is useful. But all of those are vectors. They're all vector quantities because they all have a direction and therefore can be represented by an arrow that is pointing in the direction of the vector and is a length proportional to the size of the vector. So instantaneous versus average velocity. So if we are driving towards St. Louis and our speedometer says 45 miles an hour and St. Louis is 15 miles away. So if we're going 45 miles an hour and St. Louis is 15 miles away, how long is it going to take us to get to St. Louis? So you take distance equals velocity times time, right? We talked about that last time. So you take the distance of 15, you divide it by 45, and you get 1/3. 1/3 of an hour, which would be 20 minutes. So you say, well, it takes 20 minutes to get to St. Louis. If you're going 45 miles an hour towards St. Louis, and St. Louis is 15 miles away. And my response is, nope, you're wrong, because you're going to go over the hill there by Collinsville, and there's going to be an accident, and you're going to sit in traffic for 20 minutes right there. And so your total time to St. Louis is going to be much higher. And that introduces this principle of instantaneous, right? That's what your speedometer tells you. Your speedometer tells you how fast you're going right now. I mean, that's right there in the word, right? Instantaneous, right? The word instant is right there in the word. It's what you're doing right now. And it's not necessarily what you're going to be doing 3 seconds from now or 10 seconds from now or 5 minutes from now. It's just what you're doing right now. To get an overall speed for the entire trip, that's an average, not an instantaneous. Now, yes, in theory, we could set our cruise, and our computer on our car will keep our car going whatever speed we set our cruise at. And so we might travel for minutes, maybe hours at a particular same instantaneous speed. And then our average speed over that time would be the same as that instantaneous. But that does not take into account what it took us to get from 0 up to that speed and what it's going to take to stop at the end. So the best, really the only true way to get an average velocity is to take the total distance and divide it by the total time. So, you know, you could have something like a truck driver driving across the country, right? And he drives 2,000 miles and it takes him, you know, a day and a half to do it. So 2,000 miles divided by 36 hours, you could find out what his average velocity would be for that whole trip. Now, of course, he was probably sleeping part of that time, eating part of that time, and driving part of that time. But you could establish from, say, numerous trips like that what your average velocity is, and then you could make predictions based on that average velocity. So again, that's the power of physics, is to take past data and use it to predict future results. And that's where ultimately we're going to be able to, quote, predict the future, so to speak, and know what's going to happen next. And once we have that, then we take that and we turn it into technology to solve human issues. So I have had the question before, why do we call it a speedometer instead of a velocimeter? What is really the difference? And I point out to my students that most speedometers don't work in reverse. I have found out that some of them do. It's a very dangerous thing to investigate by yourself. Much better to do if you have somebody with you. You can go to an empty parking lot, put the car in reverse, and you can look backwards as you drive backwards and have your passenger look at the speedometer and see if it comes off of 0 or not. But if your speedometer works in reverse, then the speedometer can't tell you direction, right? It doesn't tell you whether you're going forward or backwards. Now, if your speedometer only works when you're going forward, then you could argue that your speedometer is telling you both speed and direction because the direction is forward in the car. But, you know, if your wheels are turned, your speedometer is still going to read something even though your car is not going straight forward. So that's part of the reason why we call it a speedometer instead of a velocimeter, because the direction is not indicated by that dial. So velocity, how do we calculate velocity? Well, again, numerically, velocity calculations and speed calculations are the same. So velocity is our change in distance, and that's what this little triangle means, right? It's the Greek Greek letter. We use a lot of Greek letters in physics because physics is a very broad subject, and we run out of English letters is the upshot. So we use Greek letters, just like they do in math. This is the Greek letter delta, and in science, delta has the meaning, in physics in particular, delta has the meaning of change, the change. So the velocity is equal to the change in our distance divided by the change in our time. So if I'm driving along, and we have these handy dandy mile markers along our interstates, right? So if I'm at, I notice that I'm at mile marker 20 at 1 o'clock in the afternoon, and at 3 o'clock in the afternoon, I pass mile marker 130. So what is my change in distance? Well, you always take the final distance. That's very important. Deltas are always done with final minus initial, and we'll see some examples of that later on in this lecture. But your final distance was 130 miles. Your initial distance was 20. So 130 minus 20 is 110. And your final time was 3 p.m. Your initial time was 1 p.m. So 3 minus 1 is 2. So 110 miles divided by 2 hours gives you 55 miles an hour for your velocity. So that's how you do it. Sometimes you have to do the delta, sometimes you don't. Sometimes they just say, hey, you went 200 miles in 3 hours, and then they've already done the subtraction for you, and you can just plug your distance and your time in. But if they give you the individual pieces, you need to calculate the change in things. Again, the units of velocity are going to be distance over time, just like the formula implies. And this is really how we often do a direct calculation for velocity. But if we're given velocity, we're often trying to find distance instead. And in general, we don't like writing division equations, right? We'd rather multiply than divide. And so you can rearrange this equation just by taking the delta t part to the other side, right? Multiply both sides by delta t. The delta t's drop out on the right side, and we end up with a delta t on the left side with the velocity. And that gives us velocity times time equals distance, or v equals vt, which is how it'll be written on your formula sheet and how we will think about it most of the time. There is a little caveat about this. This is assuming that either your velocity is constant or you've been given an average velocity. Don't just use this with any velocity you're given, because that can cause problems. So here's a couple of practice problems that we'll work through just to get a little familiarity with this idea. So the Indy 500, of course, is a famous race held on Memorial Day most years, and it's 500 miles long. That's why they call it Indianapolis 500. So in 1988, this guy won it. His name was Rick, and he won it in 3.45 hours. So what was his average speed during the race in miles per hour? And then just to practice our unit conversion, we'll convert his miles per hour into meters per second, which will give us some idea of the relationship between miles per hour and meters per second. So again, problem solving techniques we learned in chapter 2. First thing we need to do is read the problem thoroughly, maybe a couple of times, and then we need to make a sketch. A sketch here isn't as helpful. And then we need to write down our knowns and our unknowns. So we do know that the race is 500 miles. That's maybe not obvious from the reading of the problem, but from our life experience, maybe we would know that. So the distance is 500 miles, and the time is 3.45 hours. And we want to know the velocity. That's what we were asked for, the average speed or the average velocity. So we have a distance, a time, and a velocity. And so the relationship that we're looking for is the one we just saw on the previous slide, d equals vt. We want to solve that relationship for our unknown, which is velocity. So we're going to divide both sides by t. So we get distance over time equals velocity. Now we're ready to plug our actual values into our working equation. 500 miles over 3.45 hours. And we get 145 miles per hour as an average speed, right? He's in a car designed for speed, and so that doesn't necessarily surprise us that it's a high number, right? This is a race car. Now, in order to convert from miles per hour to meters per second, as we talked back in chapter 1's notes and video, we need to have the conversion factors. So we need to have the conversion factor between meters and miles, which is 1 mile is 1,609 meters, and the conversion factor between seconds and hours. So an hour, of course, is 60 minutes, and each minute is 60 seconds. So 60 times 60 is 3,600 seconds. So those are our conversion factors. And then we go to set it up, and we want to put the miles in the denominator, so they will cancel with the miles that we already have in the numerator, right? This 145 is what we're starting with. And we want to get rid of miles because we want to go to meters per second. So we put the miles in the denominator, the meters in the numerator. And here we do the reverse. We put the hours in the numerator to cancel with the hours that were in the denominator. And when we do that, we can then cross out the miles, cross out the hours, and we'll end up with meters over seconds. But what number will we get? Well, we got to multiply across all our numerators, which is 145, 1609, and 1. So we have 145, 1609, and 1, and then all our denominators, which is 1, 1, and 3,600. So we multiply all the numerators together, we multiply all the denominators together, and then we divide them. And that gives us 64.8 meters per second. So that gives us some idea of how meters per second relate to miles per hour. Of course, you've probably never gone 145 miles an hour in a car. I certainly never have. But if we have that, right, 70 miles an hour is a much more normal highway speed. So half of 64 would be 32. So highway speeds are around 30 meters per second. And you have that again, you say, driving 35 miles an hour around town is about 15 meters per second. So that gives us some idea of common sense experience with this, these new units of meters per second. So, slowest animal ever discovered, another check problem, was a crab found in the Red Sea. It travels at an average speed of just 5.7 kilometers per year. How long would it take this crab to travel 100 kilometers? And was its speed in meters per hour? So again, another problem solving opportunity. We read the problem. Okay, this is a really slow crab. We're going to try to figure out the time for 100 kilometers. And then we're going to have to do a conversion for the speed to get it in meters per hour. So what were we given? We were given 100 kilometers is the distance. We were given a velocity of 5.7 kilometers per year. So that's nice. The distance part of our velocity matches the distance part of our distance. So we don't have to do any conversions to solve this part of the problem. And we're being asked for the time. So again, it's the because we're using an average, we can use this simple equation, d equals vt. This time we're solving for t. So we divide both sides by v. 100 divided by 5.7. Again, as we discussed in a previous lecture, when those kilometers cancel, the years end up coming up onto the top. So it takes 17.5, almost 20 years for the crab to go 100 kilometers. So I don't know how long these crabs live, but that's years. That's a long, long time. It's a very slow crab. To convert to meters per hour, we're going to again need those conversion factors. The nice thing about meters and kilometers is they're both metric units. And so the conversion's a nice, easy number, 1,000 meters in a kilometer, 1,000 meters. And how many hours are in a year? Well, a year is 365 days, and each day is 24 hours. So if we do 365 times 24, we will find out that there's 8,760 hours, 8,760 hours in a year. So now we go ahead and put those conversion factors in again so that the kilometers will cancel and so that the years will cancel. So we got to put the kilometer part in the denominator to cancel the kilometers in the numerator. Got to put the year in the numerator to cancel the year in the denominator. Those units will cancel. We'll be left with meters per hour, which is what we want. And then we multiply our numbers across and divide, and we get 0.65 meters per hour. So, if we were in class, well, especially if this was during the regular semester, when we have hour-and-a-half lectures, we would say that during the first hour of our class today, this crab would be able to travel 0.65 meters, which is roughly the width of a typical student desk. So that's a pretty slow animal to only get that far in an hour. And you might be thinking, well, what about smaller animals that that aren't as long? Aren't they slower? Well, you find actually that smaller animals tend to be faster. If you ever think about ants or spiders crawling around, they can cross your desk in a much shorter period of time than 1 hour. So that's velocity, specifically the simple problems with a constant or an average velocity. Now we're going to move on to discuss the fact that in the real world that you and I live in, velocities are rarely constant. Velocities are almost always changing. And it's very important for us to appreciate the fact that we're talking about velocity, and there's two pieces to velocity, right? There's the rate part of velocity, which is the speed part you could think of, and then there's also the direction part of velocity. As well. And in order for us to have a constant velocity, both of those parts have to be constant, okay? So, excuse me. One example that often trips people up, and again, we'll talk about this a whole lot more in chapter 9, is when an object is moving in a circle at a constant speed, because you can think of a completely circular racetrack and a car driving round and round that circle at the same speed. The speedometer is not changing, and people go, oh, well, that car is going at a constant velocity. Well, actually, it's not, because the direction that it's pointing is always changing as it goes around that circle. So to truly have a constant speed and a constant direction, you need to be on a straight, flat road with no curves and no hills. Now, living here in Illinois, we have some opportunity for that, right? There are some very flat, straight stretches of highway in Illinois, but a lot of other places you've got hills or you've got curves and that sort of thing, and so you're not keeping a constant velocity. Interestingly enough, you do not feel velocity. You cannot feel movement. A lot of us think we can, and when we're first told you can't feel movement, we go, oh yeah, I can. But the reality is you do not feel movement. What you feel, what your body can detect, is a change in movement. And again, because of the world we live in and the way we generally move, our velocities are changing all the time. So we might, in our mind, associate any movement in general with a change in velocity. But there's a number of examples, right? You can be in a car whose cruise is set. I found this experience particularly when I'm riding in a car whose cruise is set and I fall asleep. And then I wake back up and, it takes my brain a minute to figure out where I am and what's going on. And if the first thing I do is look out the window, I can be very, very confused because my body does not feel like I am moving at all. And then I think the trees are moving, which is odd. But the place where it's even more obvious to me is in an airplane, right? So you clearly feel the airplane as it takes off, right? As you rush down the runway and you're increasing your velocity, you're changing your velocity. That you definitely feel. And as they pull up and you change direction, you definitely feel that. But they get up to cruising altitude and they set that cruise, and you very quickly hardly remember that you're moving in an airplane. Your body does not feel it right now. If there's turbulence and the plane gets knocked around, then the direction gets changed some, and that you feel. And when they start to slow down to land, right? Sometimes I can be reading a book or listening to something or whatever, and you feel that slow down before they even come on the PA system to say, hey, we're approaching our destination. So you do not feel velocity, you feel changes in velocity. And of course, there's a number of ways we can change the velocity in a vehicle, right? We're all very familiar with the long skinny pedal, sometimes called the gas pedal, that we use for speeding up, which is clearly a change in our rate. We're familiar with the brake pedal that we use to decrease the rate at which we move. What people maybe are less attuned to is the fact that the steering wheel is also used for changing velocity. Now, again, velocity is the rate at which we cover distance. And the simple mathematical relationship is Vt equals d. Or as we saw it written on the previous slide, distance divided by time equals velocity. So if we take a moment to think about a graph, right? If we were to graph our location over time, as they have here on this screen, they've got the green line where we covered a lot of distance in a short time, right? They've got the red line where we covered some distance in time a little slower, and then we didn't cover any distance for a while, and then we came back to where we started. And then we finally have the blue line where we initially are covering distance at a slow rate, and then it increases as time goes on. And so if we think about it from a graphical perspective, particularly on a graph that's distance on the y and time on the x, we recognize that the rate, velocity being the rate at which distance is covered, is equivalent to what in mathematics they would tell us is the slope of the line. The slope of the line is, the slope of a line on a distance time graph is the velocity. So here we have a very large velocity on the green line, a steep slope. We're going up the hill very quick. On the red line, we have a positive slope, a positive velocity for a while, and then zero velocity, right? If you walk to your friend's house and then you hung out and talked to your friend for a while, and while you're talking to your friend, you're not moving, you have zero velocity, okay? And then your friends got to do homework, so you walk home, okay? Now you're walking back the way you came relative to our reference point. Again, we talked about frames of reference at the beginning. So if the reference point was your house to begin with, now you're decreasing the distance to your house. The distance is getting smaller. So your final distance is smaller than your initial distance. So when you do final minus initial, you're going to get a negative number. And that's going to translate to a negative velocity, and therefore, as you see here, a negative slope, because you're going back toward where you started. Now, the blue line's a little more complicated, right? The slope of the blue line is changing. And if you take a calculus class or a physics with calculus class, you will learn about that concept, how to take the slope of a curved line. It's really not as hard as it might at first sound for just a rough slope, right? You just have to consider what the straight line would be that would be touching the curve at that point, and then you take the slope of that straight line. So right here, right, we could have a straight line and we could see it would be less steep than either the green or the red line is right now. But we get up here and now we've got a straight line that's as steep as the green one, or maybe steeper. So we're not going to spend a lot of time with curved lines. We're going to stick with straight lines where the slope is easy for us to calculate. But again, the slope of a distance time graph is the velocity. It's the rate at which distance is covered. So we were talking about change in velocity. So we have a word for change in velocity. Change in velocity is defined as acceleration. Acceleration is the rate of change of velocity, right? So just as velocity was the rate of change of distance, acceleration is the rate of change of velocity. So again, it's how much does the velocity change divided by how much time did we have to do that change. So very similar looking formula to the one we had for velocity, only velocity's up here now, and acceleration is over here. Time is still down here as it was before. So A equals delta V over delta T. Now there's a fair amount of confusion about the term acceleration, and I think a lot of this confusion stems from the fact that we call the long skinny pedal, when we're not calling it the gas pedal, we call it the accelerator. And that teaches new drivers, teaches lots of people the wrong idea that acceleration means speeding up. And that is not how physics has defined acceleration. Acceleration is defined as any change in velocity, or it's defined as the rate of change in velocity. But that rate can be positive, which would be a speed up, or it can be negative, or it can be a rate at which our velocity is changing direction, in which case the size of the velocity might not be changing at all, even though there's a change to that velocity. So really, we need to think of it in that sense. It's how fast you're going faster, how fast you're slowing down, or how fast you're turning, okay? And part of this confusion, you might think, oh, well, that seems like a fine distinction. Well, it doesn't really sound like it matters very much. Well, the problem is then people, they take this word acceleration and they stick a prefix in front of it, right? A prefix that we usually use to mean not, right? So the prefix DE, right? Decelerate. So the word decelerate has entered the English language, and it's really a very inappropriate word. It doesn't make any sense with the true definition of acceleration. Well, I guess it sort of does, right? So the D prefix means the opposite, right? I'm trying to think of a good non-acceleration example of D, and I can't think of one at the moment. But you're familiar with the English language. Decelerate, that prefix means that it's the opposite of what the word was supposed to mean. So if the word is supposed to mean change, then decelerate should mean not change. So decelerate should mean constant velocity, but that's not what people mean when they use that word. They are using the wrong definition of acceleration. They're using the definition of acceleration to mean speeding up, and therefore they use decelerate to mean slowing down. And the reality is that any change is acceleration. And so de-acceleration would mean no change. And that's never what people mean when they use the word. So the word should just not be used. Now, I recognize that I can fight this fight as long as I teach, and I will never get anywhere, but I will get somewhere with my students. You will know better, even if the general public does not know any better. So acceleration is the rate of change of velocity, and there will be different sizes of accelerations, right? You can be speeding up not very much, or you can be speeding up a lot. There's different amounts of acceleration that you can have. Again, this is one of those things. I love physics because physics is so prevalent. We've all encountered it. We've all ridden in a car. Most of us have driven a car. We're very familiar with these experiences. But one of the problems with physics being so incredibly common is that people who haven't really been taught physics, they take the language of physics and they start using it however they think is correct. And then we have words like acceleration and de-acceleration, which have entered the language with the wrong definitions, and then I have to try to fix it for my students. So a simple acceleration example would include here this cheetah. So we've got a cheetah who's going to increase its velocity from 15 to 30 meters per second in 2 seconds. So what is the acceleration of the cheetah? So his velocity is clearly changing, right? It's increasing from 15 to 30. So now we're going to introduce the idea of subscripts on some of our variables. So we've got two velocities here. So we've got to have some way to distinguish between the two of them. So we have the initial velocity. What velocity did he start out at? So it says the cheetah increased its velocity from 15. So 15 was where he started, and then he ended up at 30. So that's where he ends. So we use the term initial for starting out and final for ending. So we have v with a subscript I for initial velocity, v with the subscript f for final velocity. So 15 and 30, and he did this all in 2 seconds, and we would like to know the acceleration. So again, we look for an equation that would relate these things together, and it's, of course, exactly the acceleration equation we just learned on the previous slide, that acceleration is equal to the change in velocity divided by the change in time. Now, we don't have to solve for the change in time because we were already told that the total change in time was 2 seconds. That's how long this took to occur. But we were given a final and an initial value, and so we're going to have to find the change in velocity by subtracting the initial from the final. And this equation is conveniently already solved for acceleration, A. So all we got to do is plug our 3 values in, and therefore we'll be able to get our answer. So 30 meters per second minus 15 meters per second divided by 2 seconds is 7.5 meters per second squared. Now, sometimes you're going to see this written as meters per second squared. That's how it usually gets written in the textbooks. That's what's easiest to write. But it's also very helpful to think of it, think of those seconds separately. And the reason for that is because, we might have a concept of a meter per second. Okay, so we travel a meter in a second. But the idea of a meter per second squared, that starts to escape what is our common sense understanding of the meaning of that unit. So this one's a pretty easy one for us to think about it, think it through, right? So what's going on is this cheetah is going 7.5 meters per second faster each second. So if we write it as 7.5 meters per second, that helps us to understand what's going on, right? The cheetah's going faster. So he starts out at 15, and in 1 second, he goes 7.5 meters per second faster than he was going before. So 15 plus 7.5, after 1 second, he's going 22.5 meters per second, okay? And he keeps doing that for a whole nother second. So during the second, he adds another 7.5 meters per second to his speed. So he goes from 22.5 up to 30. So in 2 seconds, he's gone from 15 up to 30. And that means that he went 7.5 meters per second faster each second, okay? It's a lot of words to talk through what's going on, but it helps us to conceptually understand what acceleration actually is. So here we got a car, right? A sports car. I don't even know how to pronounce this. It's Italian, a Bugatti Veyron. A Bugatti Veyron can go from rest to 60 miles per hour in 3 seconds. What is its acceleration? I realize that's not a terribly fast acceleration anymore, but once upon a time, going from 0 to 60 in 3 seconds was very, very impressive. So what is the acceleration of this car? So again, here's a case where we're going from rest. So that's words that should be translated into a number. So our initial velocity is going to be 0 because we're starting out at rest. Our final velocity is 60 miles per hour, and our time is 3 seconds. So we write those down: 0, 60, 3 seconds, and again, we would like to know the acceleration. So it's exactly what we had in the previous problem. So we're going to use exactly the same formula. Now you might be sitting there going, uh-oh, well, this is in hours and this is in seconds. Well, that's okay. So 60 miles an hour, final velocity, minus the initial velocity. So we have a change of 60 divided by 3. So 60 divided by 3 is 20. So we are going 20 miles an hour faster each second. So in the first second, we go from 0 to 20. In the second from 20 to 40. In the third second, from 40 to 60. So in 3 seconds, we've gone from 0 to 60 miles per hour by going 20 miles an hour faster each second. Now that's assuming we have a constant acceleration, which if you know anything about cars, they don't actually have a constant acceleration, but that's beyond the scope of this course, right? So in this course, we're assuming constant accelerations. We will never assume anything beyond a constant acceleration in our kinematics equations. So those are a couple of examples. One more acceleration example. We're driving along in our car at 60 kilometers an hour. We see a red light and we brake to a stop in 4 seconds. What is your acceleration? So I don't know if you did this with the previous two. I hope you did. If you didn't, that's okay. But again, I'd encourage you to pause the video, attempt this problem before I show you how to do it. Because we know the practice is what's going to help us to learn these skills and to be able to do problems. So what have we been given? Again, we brake to a stop, so that's 0. But this time, the 0 is the final velocity, right? We braked to a stop at the end. We were cruising along at 50. That was our initial velocity, 50 kilometers an hour. Final is 0. Our time is 4 seconds. Pull up that same equation. Stick our numbers in. Now it's 0 minus 50 divided by 4. Negative 50 divided by 4 is negative 12.5 kilometers per hour per second. Now, if you're sitting there right now thinking, oh yeah, I got 12.5 kilometers per hour per second, I did it right. I just was missing the negative sign. How big of a deal is a negative sign? Well, a negative sign is a big deal. A negative sign is enough for your answer to be wrong. Again, if you don't think it's a big deal, then let's just talk about the difference between me owing you $100 and you owing me $100, right? There's a big difference there. And I'd prefer you to owe me every time. So we have a negative acceleration because we are slowing down, because our rate of change is a decrease, right? Our rate was 60 and we went down to a rate of 0, and so that has decreased. You can think about the graph we saw a few slides ago with a negative slope, okay? So these negative signs are important and they are meaningful, and we don't just ignore them and say, oh, well, I got the right number just because my sign was off isn't a big deal. The sign is a big deal. The sign has a meaning. So we need to acknowledge that and make sure that we're doing the problem correctly. And that's where this delta V being final minus initial is really important. Sometimes we fall into the habit of going, oh yeah, subtraction, it's big minus little. No, it's not always big minus little. It is going to be big minus little if you're speeding up. That's true. You're going to be going faster later than you were initially. But if you're slowing down, it's going to be little minus big, and it's going to be negative. So you got to really keep track of what's initial and what's final. And again, you can read that out of the problem if you read the problem carefully. So again, just as we had instantaneous versus average velocity, we have instantaneous versus average acceleration. Again, the instantaneous is the slope at that particular moment on the graph. If we have nice straight lines like this, we will have an easily definable slope, and the slope will stay the same over a period of time, right? You see this line from 0 to 4 seconds, it has the same slope all the way from 0 to 4 seconds. The steepness of that line stays the same from 0 all the way to 4 seconds. Now at 4 seconds, it changes. And at 7 seconds, it changes again, right? So if we were finding the instantaneous slope at 1.2 seconds, it would be the slope of the whole line. If we were finding the instantaneous slope at 3.4 seconds, it would also be the same as the slope of the whole line, okay? But if we asked you what was the average velocity over the entire 10 seconds, well, our final velocity is 0, our initial velocity is 0, 0 minus 0 is 0, 0 divided by 10 seconds. Our average velocity, our average acceleration, excuse me, for the entire graph is 0, okay? Even though we raised our speed initially, and then we stayed at that high speed for a while, and then we reduced our speed. If you average it all together, we end up with a 0 change in our speed because we decreased just as much as we increased. So again, another graphical representation. Acceleration is the rate of change of velocity. Therefore, it's the slope of the velocity time graph. And as I mentioned already, the average is the total divided by the time. So whatever you decide that total to be, right? If you just want to know what the average is for the first 4 seconds, so then it's going to be a change of 8 minus 0 divided by 4 minus 0. So 8 over 4, that's an average acceleration of 2 meters per second, right? If you want to know what the average is between 4 and 7, 0 divided by 3, it's 0. Between 7 and 10, 8 divided by 3, it's negative 2 1/3. I believe that is maybe 2 2/3. I'm trying to do the math in my head, which is not helpful. So the relationships graphically are important. We've already talked about a couple of these. The fact that the slope of a distance versus time graph is velocity. The fact that the slope of a velocity versus time graph is the acceleration. What we have not talked about as much is the other direction. So to take the slope of something, if it's a straight line, we learned how to do that in algebra. We can take those slopes. If it's a curvy line and you know calculus, there's a way to take the slope of a curvy line as well. And the other thing you learn in calculus is how to find the area under the curve, right? So the area under the curve, if you had a line on a graph, it would be the space between that line and the x-axis. That's the area under the curve, right? So you can imagine if you have a horizontal line, that's just going to be a rectangle, right? And if it's just a rectangle, we could solve that without any calculus. We just multiply how wide the rectangle is in seconds by how tall the rectangle is in meters per second, and that would tell us the area of that space. But if we think about that for a moment, we just did velocity, which is how tall the rectangle was, times time, which is how wide the rectangle was. Velocity times time, we just learned that this chapter, actually last chapter, but also this chapter, velocity times time equals distance. So the area under the curve of a velocity time graph is the distance that you travel, right? So I'm driving along at a constant 5 meters per second. After 1 second, 5 meters per second times 1, I've gone 5 meters. After 2 seconds, 5 meters per second times 2 seconds, I've gone 10 meters. And so on and so forth for however many seconds I travel at that constant velocity. Now, if it's a diagonal line, then you have a triangle, you could still find that area. It gets more complicated if the line is a curve, admittedly, but we're not going to go there. That's calculus that we don't have to do in this course. So we've got distance versus time, we've got velocity versus time, and we'll go one more step to acceleration versus time. You can take the slope of an acceleration versus time graph. We took the slope here, it was distance divided by time. The slope here, it was distance divided by time, divided by time. Here we have distance divided by time, divided by time, divided by time. So a jerk is actually a meter per second to the third. This is a technical physics term, okay? It's not a person who's not being very polite. It is a technical term, the jerk. In fact, you can keep taking the slopes, and they're called the snap, the crackle, and the pop, the fourth, fifth, and sixth derivative of position, if you think physicists have no sense of humor. But the jerk is very relevant. The other ones are less relevant, but the jerk is very relevant to us. The rate at which your acceleration is changing is largely what causes people to get motion sickness. So it's not movement that gives you motion sickness. And it's not even necessarily acceleration that gives you motion sickness, although you can feel the acceleration. It's when the acceleration is changing. That's what gives people who are prone to motion sickness. motion sickness. If you drop somebody who's prone to motion sickness out of a plane, they will accelerate downward at a constant rate due to gravity. They will not get sick. They might get scared. They might get sick because they are scared because they're falling toward the earth, but they will not get sick from the motion, because the motion, although it's accelerating, is accelerating at a constant rate. But it's the change of the acceleration. When you're going around a bunch of curves on a road, or when you're going up and down hills on a road, then your direction is constantly changing. The direction is your velocity, and if that direction is changing at different rates, then you have a changing acceleration. Of course, one of the places people get motion sick a lot is on a boat, right? It bounces up and down, and it rocks left and right, and it rocks forward and backwards, and so you have lots of different directions of motion that are changing all the time, and that's why people get seasick, which is ultimately a form of motion sickness. So that's the slope of acceleration time, and then the area under that curve is velocity. So we take slope to go from distance to velocity, take slope to go from velocity to acceleration, take slope to go from acceleration to jerk, and then we can go the other direction. Acceleration times time is velocity. Velocity times time is distance. And when you're finding area, right, you're finding the area of a graph, you're multiplying the y value times the x value, and that's what this is, right? Y versus x, y versus x. So if we do y times x, we get the graph before, okay? And we're gonna watch a couple of videos on this. This is an important concept to help us understand how we describe motion and how motion's change is all related to one another. And so pause the video at this point. In the description of this YouTube video, there's a link to a YouTube video that I've labeled Squirrel Motion, and he's just going to explain the motion of a squirrel and what the graphs of that motion look like. We're going to do a number of these throughout my lectures, where I'm going to ask you to pause and go watch another video. If you were in class with me, I would stop the lecture and I would show you this video in class. These are very important parts of the learning. So I know there's a temptation to just be like, I'm in a hurry, I'm not going to go watch that, we'll just keep going with the lecture. But you're going to miss important pieces, and it's going to hurt you if you don't do this. So that's my warning, my one and only warning. You need to stop and go watch these videos when they come up, like this one right now. So here, similar to this squirrel video, is the idea of these three graphs that are all connected to one another, right? A position versus time graph, velocity versus time, and acceleration versus time. I'd prefer to put them vertically, one above the other, to show you the relationship, because they all have the same time axis. But there's just not enough space on the slide to do that without everything getting too small. So we're going to look at them like this. So you start here with the position versus time graph, which is actually curvy. Part of it is curvy, okay? But again, we said we can just put a straight line touching the curve and then take the slope of that line. So we can see that we start out going uphill, right? Even though it's a curve, we can see that the curve starts upward. And it starts out steeper and gets less and less steep until we end up at 0, right? So we have a positive slope, which is getting smaller and smaller until it finally comes to 0 at about right here, right? So what do we see here? That slope was positive, and it gets smaller and smaller until it hits 0, okay? Because the slope of position time is velocity, okay? And then after it hits 0, it goes negative, right? We start going downhill. If you draw a line here, you'll see that we're going downhill as we go left to right. That's a negative slope. And we're getting steeper and steeper until about here. In math, you learn this is called an inflection point, where the steepness stops getting steeper and actually starts getting less steep. So we go from 0 to more and more and more negative until we get to about here. And if we look over here at the velocity, we start at 0 and we get more and more negative until we get about here. This is that inflection point, okay? You can see it's about the first vertical dotted line, and you can see that dot's exactly on the first vertical dotted line. Now we are still negative, but we're becoming less and less negative, less and less negative. And again, I'm talking about the slope here. Obviously, this value is negative, and that's not important to us at the moment. But the slope, we are downhill, but we're becoming less and less downhill until we flatten out again at 0. And so we're downhill, which is negative, but less and less negative until we get to 0. And then from 0, we begin going into the positive again, right? Uphill. So as we move left to right and we look at the slope of this line, it's going to be uphill. And so it becomes more and more positive uphill until we get to about here, and we have increasing from 0 up to a positive number, and then it increases a little bit more. And then for this last second, we went from 0 more and more positive to here, more and more positive to here. Now we're already positive slope. Okay, and then from here to here, we increased our positive slope a little bit, but not as quickly as we were increasing before. And then for this last second, we have a constant positive slope. You see, this is a straight line again. No more curves. The first 3 seconds were curvy. The last second is a straight line, which is a constant positive slope. Okay, that's the hardest one. Dealing with curved lines is difficult. I understand. I freely will admit that. We're not going to ask you to do very much of that. I'm just trying to show you the relationship. But this next set is much easier, right? From 0 to 1 second, we have a negative slope, and we go from 1 down to -2. So that's a change of 3 over 1 second, but it's a decrease of 3. So it's -3 over 1. And that's what we get, a constant -3 over 1. The acceleration is the slope of velocity versus time. It's the change in velocity, -2 minus 1 meter per second, all over 1 second gives us -3 meters per second, okay? In the next section, we just totally undo that, right? We go from -2 up to 1. So now it's 1 minus -2, or 1 plus 2. 3 divided by 1 is +3, okay? This next section, we are still with a positive slope, but a less, right? It's just an increase of 1 in 1 second, so we have a +1 acceleration. And then finally here, the velocity is not changing. 2 minus 2 is 0. 0 divided by 1 is 0. So we have 0 acceleration there. So that's the relationship slope-wise. Now we could go back and we could do the area under the curve, right? This is 3. It's -3 units tall and 1 unit wide. So -3 times 1 is 3 units. So we should go from 1 down 3 units to -2. Okay. And here it's +3 units in the next second. So we should go from -2 up to 1. And here it's just 1 by 1. So 1 meter per second times 1 second comes out as 1 meter per second of increased velocity. So we go from 1 up to 2. And then here, there is no area under the curve, right? If the line is directly on the 0 axis, then there's no height to the rectangle, so the rectangle has 0 area. So that's what we do. It's always the area between our line and the x-axis. So if that line is below the x-axis, then we have a 0 area. Go tell your math teacher that I talked about 0 area or negative area. They'll get very excited about the fact that an area can be negative. But this is physics. Things have meaning, right? So we can go then and find the area under these curves, right? We have a small triangle here whose dimensions are not entirely clear, but there's a small positive triangle, so we go up initially from where we started. Then we have a fairly sizable negative triangle, so we go down from that point to a negative point, okay? And then we have a positive little triangle where we go up a little bit. Then we have a positive trapezoid, which is really a square and a triangle that we could calculate together, and we go up some more. And then we have this rectangle, which is 2 meters per second times 1 second. So we go up another 2 meters from this point onward. So that's slope and area under the curve. Hopefully that video was helpful. Hopefully this video will be helpful as well. Again, somebody else explaining it where it's a little easier for him to draw on the screen. Drawing with a mouse is not ideal. And so he's going to do some drawing on the screen. Again, go to that YouTube link and watch that video as he will explain on a chalkboard with a meter stick measuring the slopes in a more obvious way than I was able to do here with the mouse cursor. So I mentioned earlier that we're not going to do a lot with changing acceleration in this class. Actually, that's what a number of the later chapters are going to be all about. Chapters 6 and 7 and 8 are largely about how we avoid dealing with acceleration when it's not constant. Tricks isn't quite the right word. They're workarounds for the fact that in real life, acceleration is often not constant, and That means we have to do calculus if we're really going to analyze it from the kinematics perspective, and we don't want to do calculus, so we have other ways of doing it, so we only have to use algebra. But that's getting ahead of ourselves. My point is, for the rest of this lecture, we are going to be talking only about cases where the acceleration is constant, only where the acceleration is constant. And sometimes that constant acceleration is 0, which makes life really easy, because if, remember, acceleration is the change in velocity. So if the change in velocity is 0, then that gives us a constant velocity and makes the problem even easier. So if we have a constant acceleration, then what we are really saying is that an object has some starting velocity. That starting velocity might be 0, right? Like our race car, our Bugatti Veyron on the previous slide, which was going from 0 to 60. So its initial velocity might be 0. That's fine, but it has some starting velocity, and then it's going to accelerate at a constant rate for some amount of time. And that acceleration times however long we accelerate at that acceleration is going to change our velocity, right? Please appreciate that it's possible for this acceleration to be negative, which would mean our initial velocity plus a negative number is going to equal a final velocity that's smaller, right? As we had with the stoplight problem, 50 plus negative 12.5 times 4, 50 plus negative 50 gave us 0 for our final velocity. So this is the simple expression. If you look very carefully at it, you will notice, especially considering the two examples I just referenced, the fact that it's really just the acceleration equation rearranged, right? If I brought the VI to the other side, it would be VF minus VI. If we divided both sides by t, we would have A equals VF minus VI over t, which was our definition of acceleration. So this is just taking the definition of acceleration and rearranging it so there's no division, and putting the VF over by itself. So again, another example problem. So we got a lion this time. Again, you could pause the video, do this one on your own before I explain it. That would be useful. The lion is trotting along at 5 meters per second. When it sees a zebra, it accelerates at a constant rate of 4 meters per second, or 4 meters per second squared, for 3 seconds. What is its final speed? So we've got an initial velocity for the lion, we've got a rate of acceleration for the lion, and we've got a time. So we've got VI, A, and T, and they're asking us for VF. So that's rather nice. The givens we've been given are exactly the left side of the equation, and the unknown is exactly the right side. So 5 plus 4 meters per second times 3 seconds. So that second's going to cancel one of the seconds for the 4. One of the denominator seconds for the 4. So whether that was meters per second or whether that was meters per second squared, either way, one of the seconds is going to get canceled with the time second. So we've got 5 meters per second plus 4 times 3 is 12, 12 meters per second. Again, the units line up. That's important. We can only add things whose units line up. So we get to 17 meters per second. Again, we can walk it through because the numbers are small, and we can think about it in this way, right? So he was going 5. In the first second, he increases by 4, so that's 5 to 9. In the second he increases by 4, that's 9 to 13. And finally, in the third second, he increases by 4, that's 13 to 17. So in 3 seconds, he goes from 5 up to 17 by accelerating at 4 meters per second each second. So again, if we want to find distance with a constant acceleration, there's a couple of different ways to do it. We can't use the very simple d equals vt expression unless we're using a v that's an average. Well, how do we get the average? Well, we can get the average by taking the initial and adding the final and dividing by 2, okay? And this is a valid way to find the average if and only if our acceleration is constant, which it will be in this chapter, so we're allowed to use this expression. So if we are using average velocity, we can just use velocity average times time equals our distance. And if we substitute, right, this is one of the principles of algebra, we can substitute anything in any variable we have, like say average velocity, we can substitute something that average velocity is equal to. So if we take the right side of the equation here, and we stick it in for average velocity, then we get this expression, distance equals 1/2 VI plus VF times t. which is just sometimes an easier way to do it, right? In this one, there would be 2 steps. Find the average and then stick the average in. This one, we only have to do 1 step if we've been given the initial, the final, and the time. So if a train leaves the station with a velocity of 12 meters per second, 3 seconds later it has a velocity of 36 meters per second, how far has it traveled, assuming it has a constant acceleration? So again, this is a problem. They gave us the initial velocity, they gave us the final velocity, and they gave us the time. They didn't give us the acceleration. They didn't ask us for the acceleration. The acceleration is not really a part of this problem. We want to know the distance, and they gave us the initial and final velocities as well as the time. So we can plug it directly into this equation, which is already solved for what we're interested in. 12 plus 36 is 48. Half of 48 is 24. 24 times 3 is 72. Again, this second is going to cancel with that second, giving us an answer in meters, which is what we would expect for distance. So here's a summary of the equations that we can use when there's a constant acceleration. This is going to be a very useful set of equations. They're a little different from the ones I gave you back in chapter 2 for the problem solving equations, but these are the ones that you're going to be using in this chapter, particularly for the one-dimensional problems and for the two-dimensional problems. And it looks like there's a bunch of these, but really some of them are basically the same one done over again, right? We just talked about what the average velocity equation, where it came from. We just talked about that on the previous slide. And we talked about how this was just the average velocity combined with our basic V average times T equals D. So this one and this one we already talked about. This one we talked about 2 slides ago with the lion chasing the zebra, that our final velocity equals our initial plus AT. This was our definition of acceleration. So many of these we've talked about already. This one, which we're actually going to end up using a lot, you might want to put a bit of circle around this one or a star next to this one. This one gets used a lot. This one is simply what you get when you start out with this one down here. Distance is 1/2 VI plus VF, quantity VI plus VF times T. When you take this one and you substitute for the VF, this expression, right? If we take VI plus AT and we stick it in here for VF, we end up with VI plus VI, 2 VI, and then we have a 1/2. So 1/2 of 2 is 1. And then we multiply by that outside T. So we end up with VIT. But then we have this AT term, right? So we have AT times T. Well, T times T is T squared. And then this 1/2 comes in, and we have nothing to get rid of the 1/2. So we have 1/2 AT squared. So that's where this one comes from. Again, this one is very helpful because it will tell us the distance we travel if we have some initial velocity and we have some acceleration and we know how long we travel. So that one turns out to be very important. We use it a lot. As I mentioned here at the bottom, there are 5 variables total, right? There's initial velocity, final velocity, acceleration, distance, and time. Those are the 5 variables. And almost every physics problem, you will be given 3 of those, and you'll be asked for one of the other 2. So sometimes the quickest and easiest way to identify which equation is useful for me is to focus on the one that I wasn't given and I don't care about, right? Because there's 4 variables ultimately that they gave me, right? That, for example, in a problem like the zebra problem, the lion and zebra problem, they told me the initial velocity of the lion, they told me the final, or they asked me for the final velocity of the lion, they told me the time, they told me the acceleration. So there's a bunch of problems, a bunch of equations that have A and T and VI, and they're in multiple equations, right? But there's only one equation that doesn't have any D's in it. And notice it didn't ask me how far does the lion get as he chases the zebra. That wasn't asked for. We don't know it and we don't care. So if we don't know and we don't care what the distance is, this is the equation for me because there's no D present, right? We have to. This is the idea of algebra. We have to either know what the variable is equal to, or that variable has to be the one thing we're solving for. In a single equation circumstance, we are only allowed one unknown, and that has to be what we're trying to solve for in the problem. So stuff we don't know and don't care, we don't want it to be involved in the problem at all. So if we don't know, don't care D, this is our choice. If we don't know, don't care final velocity, this is our choice. If we don't know, don't care acceleration, this is our choice. And if we don't know, don't care time, this is our choice. All these other ones I can explain physically what is going on. This one is particularly useful to think about when you look at a velocity time graph, right? Because it's going to be a velocity time graph with a y intercept that's not 0. So you're going to have a graph. I wasn't going to do this, but I'm going to do this. You have a velocity versus time graph with a non-zero y-intercept. And that y-intercept, of course, is the initial velocity. So you end up with a rectangle and a triangle. And that rectangle has a height of vi and a width of t, so vi times t. And this triangle has a width of t and a height of vf minus vi. And if we have vf minus vi, that's equal to a times t, right? Bring the t to the other side. So we have a height that's at, and we have a width that's also still t, right? This is the t down here, the t that we're interested in. So a height of at, a width of t, so at times t, but it's a triangle, so 1/2 at times t. We'll get vit from the rectangle, and we'll get 1/2 at squared from the triangle. And that's the area under the curve, and the area under the curve of velocity versus time is distance. So I can explain these first, really the first 5 expressions. This one has no easy physical explanation. Actually, when we get to chapter 8, if I remember, I'll come back and explain where this equation came from. But the upshot of this is we solved some equation up here for t. We did algebra. We did algebra without thinking about the meaning. We solved an equation up here for t, and we stuck it into one of the other equations. And that's how we ended up with stuff that was squared, and we ended up with a factor of 2 and all of that. The nice part is it does work, okay? It does work. It's just harder for me to explain physically what's going on in this expression. So this is an important slide. You should copy it down. You should print it out. You should do something. This slide is what you're going to want with you when you go to do the homework for chapter 4, when you go to do the quiz for chapter 4, to have these available. Again, the principle of these formulas is that they are the tools we use to solve our problems. I wouldn't expect you to build me a house without a hammer or nails. I don't expect you to solve physics problems without having the formulas and a calculator with you. You're putting yourself at a great handicap, just as you would if you tried to build a house without a hammer. All right, so now we're going to talk a little bit about the one good example we have of constant acceleration in our world, right? Cars don't have a constant acceleration. Trains, planes, none of these things have constant accelerations. Even horses, if you're riding a horse, or if you're any kind of motation like that, is going to be a non-constant acceleration. But gravity is the one constant acceleration that we have. So we're going to spend a lot of time on this example because it's one of the very few ones that we have. Earth's gravitational field produces an acceleration on all masses. And we'll talk more about how the mass effect basically ends up canceling out to give us a constant acceleration when we get to chapter 5. We'll talk more about gravity and how gravity causes a force a little bit in chapter 11, as much as physicists understand it, which is not great. But the upshot is we've measured gravity all over the Earth, and we find that the acceleration of gravity, regardless of where you are on the surface of the Earth, the gravitational acceleration is pretty much the same, and it comes out to be a value a little bit less than 10, 9.8 meters per second per second. If you drop a golf ball, if you drop an elephant, if you drop a bowling ball, they will all be accelerated at this same rate. Now, they'll hit the ground with varying speeds depending on how high you dropped them from. But if you would drop all those things from the same height, then if the air resistance is negligible, they'll all hit the ground at the same rate. Like I said, all around the Earth. So what I'd like you to do now, if you have this opportunity, is to take a tennis ball, or really any ball that's reasonably soft or that you feel comfortable catching, and toss it in the air. And if you don't have a ball, toss your pencil, toss your mouse, toss something in the air, and catch it, and think about what that motion would look like if you graphed it. If you considered your hand to be the 0 point of position, if you considered the ball moving up from your hand to be going in the positive direction, what would the distance versus time graph look like when you toss a ball up in the air and you catch it? We're really focusing on one dimension of motion, right? We're focusing in the vertical direction. I throw a ball straight up in the air, it comes right back down to my hand, and I catch it. What does that look like on a distance versus time graph? What does that look like on a velocity versus time graph? What does that look like on an acceleration versus time graph? So I'm going to give you a moment, pause the video, do this, get out a piece of paper and sketch the graphs and see what you get. So this is what you would actually get if we had a force sensor. And again, I do this experiment in my high school class. We toss a ball above a motion detector and we get this sort of information, right? So when we throw the ball, initially it has a large velocity, and so it covers a lot of distance fairly quickly, but it slows down, right? Because gravity's pulling it down and it's moving up. So if it's moving up, but it's accelerating down, that's going to cause it to slow down. So it covers less and less distance until finally at the top, it stops. And then gravity has not turned off. Gravity does not care that it's reached the top. Gravity continues to pull it downward. And so now it doesn't have any upward velocity for the acceleration to be reducing. So now it starts to get downward velocity, and gravity is now speeding it up. And as it falls faster and faster and faster until it strikes your hand again, going roughly the speed that you threw it at. Which is part of the reason why taking a gun and firing bullets straight up in the air is very dangerous, because they're going to come back down at a speed not horribly different from what they went up at, and you don't want to shoot upwards at somebody like that. So we look then at the velocity graph, right? We throw it with a pretty good upward velocity, but gravity is slowing it down, right? And you can see again the relationship between the slope, steep here at the beginning, steep and positive, so a large positive number to begin with. By the time we get to the middle, we're at 0 slope, right? We're horizontal line. Horizontal line is 0 slope. And we see that our velocity at the top is exactly 0. And then we get more and more negative velocity as it comes back down to strike our hand at the same speed that we threw it at, roughly. Okay, but then if we take the slope of this line, this is a straight line. And it's a straight line with a constant negative slope. And that negative slope is, as you can see over here, a little less than -10, -9.8 meters per second squared. One of the things that confuses people sometimes, they understand that the object stops moving at the top. They understand that the velocity's got to be 0. But then they make the mistaken assumption that if the velocity is 0, then the acceleration has to be 0 as well. And you can clearly see from the graph, the acceleration at the top is not 0, right? The acceleration is the rate of change. The slope of this line does not suddenly become 0 because the value at that point is 0. The slope of this line continues to be -9.8 the whole time. If the acceleration at the top was 0 and the velocity was 0, the ball would stop moving and it would stop changing its movement. You'd throw a ball up in the air and it would freeze at the top of the toss. And we all know that doesn't happen. That is not what physically occurs. The ball doesn't even stop for a measurable amount of time before it falls right back down. So acceleration at the top is not 0. And again, we got another video of someone who's actually recorded videos of the toss and talks through the graphs and what the graphs look like with relationship to a toss or even just something being dropped. Both of those things being discussed in this video. So go ahead and watch it and then we'll continue. So we spent a bunch of time already talking about motion, and all the motion we've talked about to this point has been in one dimension, right? We've talked about cars or lions running side to side. We talked here briefly at the end about tossing a tennis ball up and down and the fact that gravity works in the vertical direction. But now we're going to talk about two-dimensional motion, right? This is where stuff starts to get interesting. If I take a tennis ball and I throw it to you sitting in the front row of my classroom, The ball is going to move up and down as I throw it to you, and it's also going to move forward and backwards as I throw it to you. So there's 2 dimensions of motion, right? If I was really sophisticated and could throw a curveball with fade, then it would maybe move in 3 dimensions. We're not going there. Not doing 3-dimensional motion, just 2-dimensional motion. And initially, you might think that 2-dimensional motion is going to be a lot harder than 1-dimensional motion, but there's some good news with respect to that. So first, let's talk about these 2 types of motion. We've got the horizontal motion. And again, we're often going to be dealing with horizontal motion that has a constant velocity, right? Here we got a ball rolling along the table. And you see the yellow arrow represents the ball's velocity. And you can see the spacing of the balls over time is exactly the same. It's traveling 2 meters per second. And there's nothing speeding up or slowing down the ball. Now, I'm not going to sit here and tell you that horizontal motion in our world is not accelerated. There's a lot of accelerated horizontal motion, but none of that acceleration is very constant. So we're going to focus on things like a ball rolling across a frictionless table where the ball just keeps going at the same speed. So that's going to be really nice because we can use this simple expression, distance equals average velocity times time, because if the velocity is constant, then whatever velocity we have is also the average, right? 2 plus 2 plus 2 plus 2 divided by 4 is still 2, right? So the horizontal motion is often with no acceleration. On the other hand, the vertical motion has a constant acceleration, which is gravity, and we're familiar with that, right? And that's pretty much the acceleration we're going to deal with all of the time. So here we have a ball that is moving vertically. We're dropping it off of a table, right? And it's starting from rest, and you can see from the motion lines that it's going faster and faster. You can also see from the distance covered between subsequent balls that it's going faster and faster because it's covering a greater and greater amount of distance. Whereas here you see the ball covers the same distance each time. So a little bit more complex expression here. Again, another one from our previous slide of equations, but one that we can handle, especially since the acceleration tends to always be the same value, and we know what that value is. So the independence of perpendicular motion, that was the title of the last slide, and I got a flag there to drive home this principle. This is why 2D motion is not that difficult, because it turns out that the 2 dimensions don't care about what's going on in the other direction. And there's a classic physics experiment in which we demonstrate this idea, and that's the idea of the bullet fired and the bullet dropped, which we're going to talk about here on the next slide. So this is why we had that whole chapter 3, about resolving our vectors so that we can treat the horizontal and the vertical pieces independently, okay? Because let's say we have an object that we throw at some velocity at an angle, right? Let's say I'm a soccer goalie and I kick the ball down the field, right? I'm not going to kick it straight up, and I'm not going to kick it straight horizontal. I'm going to kick it at some angle down the field, okay? So we want to know, where's that ball going to land if I kick it at this velocity and this angle? Well, that's a bit of a problem if we try to study the black vector directly, right? Because gravity is accelerating downward, but gravity is not accelerating sideways. And so that's a challenge. But what we find is if we take the black vector and we split it into these green vectors, now the horizontal velocity can ignore gravity because gravity doesn't work horizontally. And the vertical velocity can fully engage gravity because gravity is working completely in the vertical direction. And so we can solve the problem by working with the 2 pieces on their own. So that's the power of independence, right? Perpendicular independence. And that's what we have found. It's not like we set it up this way because we wanted it to be that way. Again, we don't write the rules in science. We study nature. And this is the way nature is set up, that the vertical does not care what is going on horizontal, and the horizontal does not care what's going on vertically. They're totally independent and unaffected by one another. There's an aspect where they are connected, right? The time in the air connects them, right? When the ball falls back to the soccer field, it's going to strike the ground and it's not going to be able to go any lower, and that's going to create a great increase in friction on the horizontal motion and cause it to stop. So they are related via the time, but while they're in the air, they don't care what's going on in the other direction. So the famous physics experiment, of course, is about bullets, right? So if I have a bullet and I shoot it horizontally straight out of a gun, and if I have a bullet that I hold at the same height as my gun, and the same time I pull the trigger, I drop that bullet, which one's going to hit the ground first? And it's a classic physics experiment. Of course, I'm not going to bring a weapon into class. That would be unacceptable on a number of levels. But this has been done by other people, right? And most good physics experiments have been done amongst other people by the Mythbusters TV show. So that's what I'm going to have you go watch right now. It's called Mythbusters for People in a Hurry. It's only a 3-minute video, not a 50-minute video. But I want you to go watch the experiment they do where they fire a gun horizontally and they drop a bullet. And using their high-speed camera, they show you what happens in terms of which one hits the ground first. And people have different ideas about which one should hit the ground first. But go and watch the video and you'll see which one hits the ground first, and then come back and continue here. So there is true independence, right? The bullet doesn't care whether it's shot at high speed out of the end of a gun or whether it's dropped with no horizontal speed. It will hit the ground at the same time either way, as they showed you that they were hitting each other so closely together that it was indistinguishable to the human eye. And here's the same experiment done with a little bit different technology, right? Here there's a red ball that's dropped and a yellow ball that's shot sideways at the same time, and they have a strobe light, so they're effectively taking a picture every time the strobe light flashes. And you will, so these are essentially a whole bunch of pictures of the same ball. But you will see that the two balls stay at the same vertical height all the way down until they strike the ground, even though this one has a sideways motion and this one does not. So the way gravity pulls you to the ground does not care whether you're moving sideways or not. In fact, it goes further than that, right? So it doesn't even matter whether you're being shot straight horizontal or not. You're going to fall in the same way as if you were dropped from some point along that line. So there's a video here to demonstrate this, another classic physics experiment. This one I think is being done by the lab techs at MIT. Might not be MIT, I don't remember exactly, but it's a great video to show you what happens when they point their spring-loaded cannon up in the air at a monkey, and the monkey lets go of the tree at the same time they shoot at the monkey. Now, of course, this doesn't quite relate to genuine hunting because usually the animal doesn't drop the moment you pull the trigger. So when you're actually shooting a weapon, you need to aim a little above your target because your bullet will fall and your target presumably will not. But pause the video, go watch the shoot the monkey video. This is not a real monkey. No monkeys are going to die. It's a stuffed monkey. But go ahead and watch the shoot the monkey video and then come back and we'll continue. So here's a schematic of these problems and how we're going to ultimately solve them and deal with them. So we got a ball that rolls off the edge of the table, and it's going to follow the solid line path that you see through the middle of the picture. And the velocity of the ball as it falls is going to be those progressively longer red lines, right? And so those red lines, not only is it changing length, but it's also changing direction, right? Here it's a little more horizontal, and now it's more vertical and even more vertical. And so how do we deal with this? It just looks nasty. We're on a curve. Are we going to have some kind of equation for a parabola? It's all kinds of nastiness. But we don't have to deal with the red lines at all. We are going to be able to escape them completely because of the independence of the horizontal and vertical components. See, the way they drew this shows you that the ball is actually acting in the horizontal direction as if it's still on the table. It's still traveling with that constant 2 meters per second horizontal velocity, and it will keep doing that until it hits the ground. And vertically, the ball is acting just as if we dropped it off the edge of the table, okay? We looked at those two motions independently. Now we look at the motion of the ball with those two motions combined, and we see that it's doing the same thing, right? It's just as far over here as it is up here. It's just as far down here as it is over here. So we don't have to deal with them both at the same time. We can deal with them separately and just put them together where they need to come together. And that's how we're going to do these problems. So let's talk about launches. That soccer goalie who was kicking the ball down the field, or the football player who's punting the ball down the field, or the artilleryman who's trying to fire a shell as far into the enemy's lines as possible. So what would be the best angle? Two thoughts come to people's minds. One thought is, well, we should shoot it pretty much straight up in the air because that would give us lots of hang time, right? But the problem is if we shoot it straight up in the air, we have a large vertical component, but we have a very small horizontal component. So then sometimes people go the opposite direction and say, well, we should shoot straight sideways because then we have a large horizontal velocity. Well, that's true, but then you're not going to stay in the air very long before you hit the ground, and then your shell's going to stop or blow up or whatever. So it's not straight up, it's not straight sideways, it's actually halfway in between. So the theoretical best angle is 45 degrees. And in addition to that, we have found that complementary angles, right? The complementary angles in mathematics, our definition of complementary means they add up to 90 degrees. Complementary angles will land you in the same place. The complement of 45 is 45, so it will land you at the furthest distance. But if we shot it at straight up 90 degrees, it would actually go nowhere. And if we shot it at 0 degrees, it would go nowhere. Both of those would be nowhere. If we shot it at 85 degrees, it would travel just a little distance. And if we shot it at 5 degrees, it would travel just a little distance. I'm tired of explaining this. Let's look at the picture. So here you see at 75 degrees, we have a lot of hang time and we come down and we land. 15 degrees, we have a lot less hang time, but we end up landing at the same spot as the 75 degrees. And you can see these different angles. 45 will actually send us the greatest possible distance. Theoretically, right? In the real world, especially when we're firing artillery shells at high speeds, the faster you go, the more air resistance has an effect. So in the real world, at higher speeds, the best angle is actually a little less than 45. It's actually about 37 degrees is the real world best angle, but that's not important. We're not going to do any calculations where you'll need the real world best. Just appreciate the fact that complementary angles will land you in the same spot. 75 and 15, same spot. 60 and 30, the same spot. 45 and 45, the same spot. 90 and 0, the same spot. Again, it all depends on what your goal is. This is assuming your goal is the greatest distance or range down the field. If your goal, for example, in football, you might be punting it to try to have a lot of hang time so that your cover team can get down, then you would kick it at a different angle. And again, this is another type of two-dimensional problem we're going to do. We talked about the ball rolling off the table. I call those cliff problems. And then we're going to talk about problems like this, which I call projectile launch problems, where we kick them up and forward at some angle, like on a soccer or a football field, and then we have to figure out where they're going to land. One thing I would point out to you about this is the red arrows, it's symmetrical, right? And at the very top, the red arrow appears to disappear, but that's because the red arrow is underneath the yellow arrow, right? When we tossed the tennis ball straight up in the air, it had no vertical velocity at the top of its path. And the same thing is true of this projectile. No vertical velocity at the top of the path, but there is a horizontal velocity, okay? So it is still moving horizontally at the top of the path, but it's by far the smallest of any velocities it has because it does not have a vertical part to add to the triangle. There's just the horizontal part. So now I'm going to work through 3 practice problems of how to do these two-dimensional ones, and then there will be a worksheet of additional two-dimensional practice problems, and will be a second PowerPoint in the folder on Blackboard. So after you try the practice problems, you can open up that PowerPoint, and similar to this PowerPoint, to these slides, it will go through all the steps of doing the problem. So if you don't get it correct, you can work through those steps and see where you went wrong. So here we've got a problem. A cliff diver runs straight off the cliff at 8 meters per second. Straight off the cliff, 8 meters per second. If the cliff is 20 meters high, how far out from the base does he land in the water? So this is a cliff problem. It's a two-dimensional problem. He's running with a horizontal velocity, but he's going to fall a vertical distance. So how do we do these problems? So this is, again, a lot of times in physics, the key is to be organized in terms of your approach to a problem. So this is my organizational device for doing two-dimensional kinematics problems. I call it a T-chart, right? So if you look at these solid black lines, it forms a T. And the reason I make a T-chart is because there are two dimensions involved, right? There's the vertical dimension or the Y dimension, and there's the horizontal dimension or the X dimension. And it's extremely important that I keep my data and my information separate, right? Because all those equations that I showed you on a previous slide, those are all one-dimensional equations. We don't really have two-dimensional equations. We have one-dimensional equations. We do a two-dimensional problem by splitting it into two one-dimensional problems. So those equations work great as long as we are only putting information from a single dimension into them. So I make this chart to keep myself straight, okay, so that I don't get confused. Because see, I might sit there and go, oh, well, that's a distance and that's a velocity, and I just need to find an equation that has distance and velocity in it and stick those two numbers in. If you do that, you're going to end up toast, right? Because this is a vertical distance and this is a horizontal velocity. So that's not going to work together. So we've got this chart. We got a vertical distance, a vertical initial velocity, a vertical acceleration, and a vertical time. And then we have the same things for horizontal. So we have a total of, it appears, 8 variables. In fact, there aren't 8 variables, right? Because the line does not go all the way to the bottom. It does not go down to the times. The times are equal to each other. That's how we're going to get connection. That's how we're going to go from one side of the chart to the other side of the chart. So we don't actually have 8 variables. We have 7 variables, okay? And what we need to do is start filling in this chart with the stuff that we know and the stuff that we know we don't know, right? What is the unknown? How far from the base does he hit the water? That's our known unknown. We know that that's what we're not supposed to know. But everything else we need to know except for the time, right? So if we know the top 3 on the Y side, we could use them to solve for the time, and then we could use the time and some other information to solve for an unknown on the X side. Or maybe the other way around. We'll do problems that work in both directions. But the upside is that we need to know 5 of the 6 values in the top, and the last one needs to be the thing that we're solving for. So that's a little challenging because we look at this problem and we go, huh, well, he says I'm supposed to know 5 numbers and they only gave me 2. How in the world am I going to do this? Well, the first step is to stick those 2 in the right places, right? So a cliff diver runs straight off a cliff. So the picture helps us a little bit with this. That 8 meters per second is a horizontal velocity. He's running off the cliff with a horizontal initial velocity. So we're going to stick the 8 in here by the initial velocity for the X. Okay, that's where the 8 meters per second goes. And then if the cliff is 20 meters high, how far from the base does he hit the water? So this is a cliff height. So it's a vertical distance, and we're going to go down 20 meters. So we need to make that a negative 20 because we're going to fall 20 meters, okay? So now we filled in 2 of the 5 spots, okay? And then how far from the base does he hit the water? So our unknown, our question mark is going to be how far from the base. So that's a horizontal distance. So we don't know D. D is my question mark, okay? So I've got negative 20, I've got 8, and I've got question mark, okay? So that leaves me 3 more things that I need to know, okay? So how do I figure out what those 3 things are? Well, I've already showed you what the values are, but let's talk about how you come up with those. Again, for a physicist, one of our favorite numbers in the entire lexicon of numbers is the number 0, right? Because anything times 0 is 0, and that's going to make the problem easier. So you'll see 2 of the 3 numbers that we had left turned out to be 0. So the cliff diver is running off the cliff. Now, whether he waves his arms or not, he's not going to be able to accelerate himself. He's not going to be able to speed up or really slow down his horizontal motion. He doesn't have a rocket pack on. He doesn't have a propeller or wings or any of that sort of thing. So his horizontal acceleration in the air is going to be 0. On the land, yeah, his feet can accelerate him. But once he's in the air, his feet aren't going to help or hinder him. So the horizontal acceleration is 0. And I'll give you a hint. In this class, the horizontal acceleration is always going to be 0. Okay, we don't have constant accelerations that we're familiar with on Earth. And so the horizontal acceleration in the air is going to be 0. It's actually part of the definition of a projectile. A projectile is an object flying through the air only under the influence of gravity. So by definition of something being a projectile, its horizontal acceleration is going to be 0. And its vertical acceleration is going to be that of gravity. Now, again, gravity pulls us down and the downward direction is negative. So it's extremely important that this 20 and this 9.8 are both negative. If you screw up and they're both positive, you'll get away with it. But if you screw up and one's positive and one's negative, you'll end up with imaginary numbers, and that's not a place where you want to be. So that explains the acceleration row, which you will almost always have to fill the acceleration row in from your own mind, from your knowledge that the problem is happening on the Earth, and on the Earth, the acceleration of gravity is this, and the horizontal acceleration will be 0. That's just what you're supposed to understand as a student of physics. Again, in my mind, filling this chart out is the physics of the problem. You read the problem. If you can get this chart filled out, from here on, it's just algebra. It's just math. It doesn't require physics thinking. But filling out this chart does require physics thinking, like recognizing that there's not going to be a horizontal acceleration, recognizing the vertical acceleration is from gravity, and recognizing that if he ran straight off the cliff, he did not jump up off the cliff. He did not dive down off the cliff. He ran straight off the cliff, which means all his velocity was in the horizontal and none of it was in the vertical. Really, could he have kind of done a jump hop off the cliff? Yes, he could have. But if I give you a problem like that, I'm going to have to tell you the angle that he jumps off of the cliff so that you can divide the velocity into the two pieces. So if you don't see an angle, it's very reasonable to assume that all that velocity is in the horizontal and none of it's in the vertical. So that's how we get that last 0. So now we know vertically he's going to fall a distance of 20 meters. He doesn't have an initial up or down velocity, but he does have gravity. So we have 3 numbers there, d, vi, and a, and we don't know t. So if we can find an equation with 4 variables in it, right? And what did I say back on that equation slide? There's 5 variables. You'll be given 3. You'll be asked to solve for a 4th. So if we use the y information to solve for time, we can bring the time over here and use the time to solve for the distance and solve the problem. So we are going to have to do, it's a 2-dimensional problem. We're going to have to do 2 problems, but they're going to be 2 1-dimensional problems. And it turns out we're going to use the same equation. We're going to use the same equation twice, once in the y and once in the x, right? Because these are the same set of variables. And so we're going to use the same equation each time. First, we're going to do the blue equation for the y. So I just took this equation right here, d equals vit plus 1/2 at squared. Again, this was the right equation because it has a d, a vi, a t, and an a, and those are exactly the variables that I have and that I want to know. So now I'm just going to substitute in. -20 goes in for the d, 0 goes in for the vi. I don't know the t. The 1/2 is set, the a is -9.8, and I'm supposed to find the t squared. So we move on a step. 0 times anything is 0, so that term goes away. Yay, my life gets easier. Half of -9.8 is -4.9. So now I've got -20 equals -4.9 t squared. I divide both sides by the -4.9. 20 divided by a little less than 5 is a little more than 4. 4.08 equals t squared. I take the square root of both sides. The square root of 4 is approximately 2. So I come and fill that into my chart. 2.02 seconds from my y information. So 2.02 seconds from my x information. Now I can go back and use this same equation, but this time in red, with all of this information. It turns out to be even easier. My initial velocity is 8. My time is 2.02. I have 1/2, but then my a is 0. Okay, technically my time is 2.02 squared, but 0. As soon as I see a 0 in a term, what do I know is going to happen to that term? I know it's going to disappear. 0 times anything is 0. So we end up only having the first term to deal with, right? Again, this is, in a sense, non-accelerated motion. Our initial velocity is also my average velocity. It's just average velocity times time equals my distance. So 8 times 2.02, he's going to land 16.2 meters away from the base of the cliff. That's my answer. I answered my problem. It sounds like a reasonable distance for a cliff diver running off the cliff at almost 15 miles an hour. He's a fast runner. Okay, so that's the first problem. I walked you through this one entirely because we hadn't done one like this before. Now we're going to do another one. I would encourage you to take a moment, pause the video, draw yourself this T-chart. and see how you can do filling in the t-chart and solving for the answer before you continue playing the video and watch me explain the problem. So it's another cliff problem. The car is found 35 meters from the base of a 15-meter tall cliff. The police asks you how fast it was traveling when it went off the cliff. So we've been given two distances, and that's all. How far away the car landed and how tall the cliff was. So we can stick those two numbers in, negative 15 for the height of the cliff and 35 for the distance. We want to know how fast it was traveling when it went off the cliff. So that's, again, assumption that we're going to go straight off the cliff. So that's a question mark for the horizontal or the x initial velocity. That's my question mark. As we discussed extensively in the last slide, the horizontal acceleration will be 0. The vertical velocity will be 0. The car doesn't jump off the cliff. It doesn't dive off the cliff. It goes straight off the cliff. So the vertical part is 0, and the vertical acceleration is negative 9.8. So we should have gotten these numbers in the chart. Take a moment, look at your work. If you didn't get these numbers in your chart, the odds of you getting the right answer are extremely small. So again, in my opinion, this is the physics part of the problem. Reading the situation, thinking about it, and filling in the chart. Once the chart is filled in, we just do algebra. Now, if your chart is correct and your answer isn't, then we have an issue somewhere in the algebra, and you need to check how you did for math. Slightly different problem than the last one, but really not very different. Again, we have the y information. We're going to use that to find the time, and then use the time to find the critical x component. Again, these same variables, same equations. Again, I know the first time we do a problem like this, it's just like, whoa, there's so many parts. How am I ever going to keep this straight? But the reality is we do the same, similar types of problems over and over again. So the second, third, fourth, fifth, sixth, 107th time you do it, it will get easier. No, I promise, we won't do 107 of these problems. So we use the y values in the blue equation. The cliff is 15 meters high, so negative 15. We have 0 initial velocity. Again, so 0 times anything is 0. 1/2 negative 9.8 is the acceleration of gravity with our t squared. So again, we have negative 15 equals negative 4.9 t squared. This time, negative 15 divided by negative 5 gives us a little more than 3. The square root of 3 is 1.75 seconds. So that's the time it took us to fall down the cliff. So that's the time the car had to move horizontally away from the cliff. Now, if it landed this far away and it had this much time to travel, how fast would it have been going at the top of the cliff? So now we've got these three numbers with this unknown, and we can plug it in. So 35 is how far from the base we were. We don't know what the velocity is, but we know it traveled for 1.75 seconds. And again, this whole second term disappears because the acceleration is 0. So we do the 35 divided by the 1.75, and that gives us an initial velocity of 20 meters per second, which is, what did we decide that was? 45 miles an hour. Depends what the speed was on that road. But that's not our job. Our job was to tell the policeman how fast they were going. They were going 20 meters per second. He can decide from here what's he going to do with that. So second cliff problem, again, primarily we're going to do two types of projectile motion problems. Cliff problems and soccer ball problems is what I call them. And so we've just done two cliff problems, and now we're going to do a soccer ball problem, or in this case, a rocket problem. So we've got a toy rocket launched on level ground at an angle of 35 degrees with a launch velocity of 14 meters per second. How far from the launcher does it land? So that's the question this time. We haven't done one like this, but you can pause the video, give it a shot on your own. If you can't figure this out, that's not surprising. We haven't done one quite like this. You will do multiple ones like this on the practice sheet that's in the Blackboard folder. And then there will be further explanation of how to do them in the PowerPoint that goes with that. So same chart, same approach. Again, we need to fill in 5 of the 6 blanks up here, but that appears to be even harder because now they gave us an angle, and none of these are for an angle. They did give us a velocity, so where should we put the 14? Should the 14 go here, or should the 14 go here? And I don't know which one you answered, but it should not go for the X and it should not go for the Y, because that 14 is neither all X nor is it all Y. right? This is why we did chapter 3, vectors, right? We're given an angle and we're given the launch velocity, right? We're going to launch it at this angle at 14 meters per second. So now we have a triangle, and our job is to split the triangle into a horizontal part and a vertical part so that we can use those values to solve the problem. Okay, so here's our angle. It's an angle. When they say launch angle, they mean measured from the horizontal. So that's where our angle is going to be. So 14 times the cosine of the angle will give us the adjacent side, which will be the red or the x or the horizontal value. And then the opposite side will give us 14 sine of the angle will give us the vertical. So that will give us those two numbers when we plug that into our calculator. So that's two of our numbers. How far from the launcher does it land? That's our horizontal distance. That's what we're trying to find. Our acceleration rho, we already know, is 0 and negative 9.8. So what is our vertical displacement? That's the question. How far are we going to displace vertically? And this is, in my opinion, the hardest part of this problem is figuring out what goes in that blank and why the number that goes there goes there. So we can think of the motion of the rocket, right? It's going to rise up in the air and it's going to come back down and it's going to strike the ground, okay? And we were told that it was launched on level ground. So here's where the distinction between distance and displacement is important. And I've probably been too lazy in my speech this whole lecture, and I've been saying distance when I've really been meaning displacement. But the displacement, the distance from the ground at the end is going to be 0, right? We're going to be back at the same vertical location that we started at. So the vertical displacement will be 0. We'll be back on the ground. Yes, in the middle, we'll have a great big vertical displacement. We'll be way up in the sky. But at the end, which is what we're asked for, how far from the launcher does it land? At the end, we're back where we started vertically, okay? So this vertical displacement is 0, okay? And that's why it is. And if you don't completely grasp that right now, I understand. Think about it some more. Go back and listen to what I said again. And try to visualize what's going on, and hopefully it will make some sense. So we solved these with our calculator. 14 cosine of 35 was 11.5. 14 sine of 35 was 8.03. And then, like we said, the accelerations and the distances. So again, we have all the vertical information to find the time. We're going to use that time to find the unknown on the x side. We plug our values in. You'll notice this is a little bit repetitive. We've done it now 3 times in 3 slides. Actually, it's a little different this time, right? Because the 0 is in a different place. If ever we don't have a 0 in the vertical information, then we have to solve a quadratic equation, which can be done. You probably learned how to do that in algebra about the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. But we don't have to do that as long as we have a 0 somewhere. And this time we had a 0 as our distance, right? So this was negative. When we add it to the other side, it becomes positive, right? If you add something, it eliminates the negative, and so we're just going to move the 4.9 t squared to the other side and thereby get rid of the negative sign, right? Because here we have one negative, but the other is not. We're shot upward, but gravity is pulling us downward. So one of those is negative, one of them is not. So our ability to move it to the other side of the equation eliminates the negative. And then we have a t squared on one side and a t on the other. Technically, we shouldn't just divide by the t. We should factor the t out and acknowledge that one of the solutions to this quadratic is the solution of t equals 0, right? The rocket is on the ground at t equals 0 right before we launch it. That's fine. We know that. What we're interested in is what's the other time that it's on the ground, right? What we're really looking at here is an upside down parabola, okay? And we're saying, when does this parabola meet the ground, which is y equals 0. So y equals 0 at what x values? Well, y equals 0 at the x value or the t value of 0 before we launch. But it also equals 0 at some later time when the rocket comes back down. And that's the one we care about. So we factor out t equals 0 and we eliminate it as a solution. And what we have left is 8.03 equals 4.9t. Divide both sides by 4.9, and t is 1.64. When the rocket comes back down, it's going to be 1.64 seconds after launch. So that's our time. Bring our time over here. Again, with 0 acceleration, it's just a matter of our velocity times our time equals our distance. Okay? So again, strongly recommend that you go ahead and work on those practice problems from the Blackboard folder right now, and then look through the PowerPoint that goes through all these steps for those as well. It's not a narrated PowerPoint, but it has all of these, all the math is shown to you there just as it was shown on these slides. And then you'll have more practice on the homework and more practice on the quizzes. But this is kinematics. This is the basic of describing motion, and we want to be able to describe it effectively before we move on to chapter 5, where we start talking about the causes of it. And so that's where we are. So that's the end of chapter 4. No, it was a little bit of a long video, but I'll see you back for chapter 5.